This is the geometric solids activity. We'll make various geometric solids out of straw segments and pipe cleaners. This is a tetrahedron, and as you can see, it's completely symmetric. Every vertex is the same, every edge is the same, and every face is the same. You can turn it around any different direction and it's all the same. That means it's symmetric and it's a regular polyhedron. Polyhedron means many faces. Got all these faces. That's from Greek. And they're made from polygons. You can count the vertexes. The plural of vertex is actually vertices. You can count the vertices on here. You can count the faces, you can count the edges, and you can count how many edges are coming together at a single vertex. You can see that's 3 on the tetrahedron. But before we analyze them anymore, let's learn how to make one. So if you get a pipe cleaner and then you decide which polygon you'll have as your face, and you put the straws onto the pipe cleaner, make sure that they're all about the same length. If they're not the same length, then it's not going to be a regular polygon and it won't be one of these classic polyhedra. It'll be a fine solid, even if it's not the same length, but we'll try to make these regular if we can. So there's our polygon. Happens to be a triangle, 3 sides, almost regular, and it sits flat on a table. That's 2-dimensional. That's what a polygon is. Polygon means many angles. We've got 1, 2, 3 angles. So that's 2-dimensional. When we put the rest of it on, it's going to stick up like this one, then it's going to be 3-dimensional. Right, so if you've got a little piece sticking off here, then you can start the next part with that. You could put another segment on there, and if you're clever, you'll cover up that last one that was down there when you go down the other end, and you put another one on the top. And if it reaches, you're golden. It reaches down to this little vertex over here, and you wrap it around twice. And you can leave it hanging out because you never know what you're going to need. And now you can see that we're just missing one edge there. So you get another pipe cleaner, whatever color you want, and you can wrap it around. You can wrap it around just once is good enough, and make it come up parallel to the other one. Then you slide your segment on, and it goes down there and goes up to the other vertex, and then you wrap it around. Wrap it around once, maybe twice, then this one happens to be done. Then you can decide what you want to leave hanging off. You can leave it hanging like that with a little hook so you can hang it up, or you could cut it off. You could put a string on it, and then you could cut off the ones you don't like, the ones you don't want, you cut them off, or you could just keep on wrapping them around until they disappear. Once you cut it off, it's a little bit sharp. Be careful about that. So there's your tetrahedron. All right, now there's another way to add additional segments, and I'll show you that. I'm gonna make another one now. It's called a rhombocuboctahedron. It's an Archimedean solid, not one of the Platonic solids, just to show you another way you can do it. So I'm going to start with a square. This one's made of squares and rectangles. All right, so you got a square. I'll do the same thing. Tighten it up pretty tight. No, not that tight, doesn't matter. And now you see there's not enough. There's not going to be enough to go around again. So I'm going to have to get another piece. And I'm going to get another piece like this, and now I'm going to thread it through there. So now you can see it's got a different look. That straw's got 2 different colors to it. That's kind of nice. And with the rhombocuboctahedron, I'm going to make triangles around the square. All right, so I got, I'm gonna put 2 on and then bend it down there. Oh, that one's a little bit too long. If it's too long, you need to cut it so it's the same as the others. Need to be almost the same length. All right, and then I'm gonna twist it together like that. Now I'll do the same thing on the other side. All right, there's my rhombocuboctahedron, made with only squares and triangles. And every vertex has four edges coming out, but some of them have 3 squares and a triangle. Actually, all of them have 3 squares and a triangle. 3 squares and a triangle. 3 squares and a triangle. Now some of the squares have 4 squares around them. 1, 2, 3, 4. And triangles at the vertex. But other squares have 2 squares and 2 triangles around them. And squares at the vertex. Saw is all very interesting things you can do to analyze it. You saw when I was making this, if you watched it, I screwed up several times. And when you screw up, you can always find it because you've broken one of the rules. When you're going through these, you follow basically 2 rules. One is that at every intersection, every vertex, there's the same number of edges. That's the rule for the project. This is a dodecahedron. It's got 3 vertexes at 3 edges at every vertex. And And the other rule is the face, the shape of the face. This one's all pentagons. So if you're making it and you got a hexagon in there, you know it's wrong. Or if it's a square. So this one, this is the dodecahedron's only got pentagons, so it's easier in that sense. The 5 platonic solids are easier. There's only one shape. But the Archimedean solids, the other solids, you have, when you're making it, you have to work it out. Like this one that has the rule where there's 3 squares and a triangle at every vertex. Now here's a cuboctahedron, also made with just squares and triangles. And every square has got 4 triangles around it. Every single square is the same. It's got 4 triangles around it. And every triangle is the same. It's got 3 squares on the edges and 3 triangles at the vertex. So you can see they've all got a pattern, and when you screw up, you just miss that pattern. You can see that only on these green squares did I use that method where I put the pipe cleaner all the way through the new, and that was just to make through the 4 segments. And the benefit is then you've got these colors, the 4 colors there. All the rest of them, I used the other method where you just twist on the vertex you want and start running it around wherever you want it. That's one way you can make it nice colors. And you'll see the pink here. The pink was the original square that I made. That's down at the bottom. I just kind of left it there. So you can put that one at the bottom, and you see these 4 other green squares on the top. Then you can tie it on wherever you want to hang it. Okay. So then if we were to count this, it's going to be a little bit difficult. How many squares are there? Well, it's hard because you can't mark them. Well, you can mark them, but it's not that easy to mark them. So it's good to use symmetry. Now, I noticed when I was building it that there's this wall of squares all the way around the edge. So I'm going to count everything above that wall, and then I can double it because the bottom is going to be the same. All right, so up on the top here, I got 1, 2, 3, 4, 5 squares. So that means there's 5 squares on the bottom too, that's 10. And then I'm going to go around the outside and I see 1, 2, 3, 4, 5, 6, 7, 8. 8 squares. So I got 10 plus 8, that's 18 squares. And the triangles, there's only 4 on top here and 4 on the bottom there. So there's 8 triangles. Now you can mark them with tape if you want. It's a little bit, it's a drag. There's one, there's another one here. Or you could just mark one place, like I'm gonna start with this square, and I'm gonna put this one on the bottom, and then I'm gonna count around that one and not move it. Otherwise you lose track of which one you started with. So that's one way. The edges you can mark. You can just get a marker and just start marking them. 1, 2, 3, 4. Just start marking them until you counted all the edges. That's to fill out the table. The table is very interesting. You can check it out on the write-up. The table's got how many sticks are each vertex, how many faces, how many vertices, how many edges, and then if it's got a name. And some of the more complicated ones, you probably want to go get a picture of it on the internet or in a book. You can find the pictures of these things. I had the picture of this one. This one's a very interesting one because in 2009, somebody realized there's another way to put it together. You can have that, and then either the top or the bottom, you can rotate it one section. And then it's still a rhombocuboctahedron, but some things have changed. Now it's not as symmetric, and mathematicians are arguing about whether it's an Archimedean solid or not. That would be the 14th Archimedean solid. But anyway, these are the Archimedean solids, the rhombocuboctahedron and the cuboctahedron with just squares and triangles. Then we've got the this is called a icosahedron because it's got parts of both the icosahedron and the dodecahedron. That one's made with pentagons and triangles. It's also completely symmetric around the pentagons. Every pentagon has just got a bunch of triangles around it, and when you're done, you've got an icosahedron, which, you know, everybody should have, shouldn't they? And then this is the most famous one. This one is a soccer ball. This is the buckyball. It's called after Buckminster Fuller, who used to build houses like this, or design houses anyway. Geodesic domes. So this one's made with pentagons and hexagons. It's quite interesting. Point this out to every soccer fan you know. The pentagon is surrounded by hexagons, but a hexagon is surrounded by 3 hexagons and 3 pentagons, and that makes it. And at the intersections, at the vertices, there's only three segments coming together, and every segment is the same. It's got 2 hexagons and a pentagon. So that's all very interesting. So let's go all the way back to the 5 Platonic solids, which you can start with because they're so elegant, they're so mystical. There's only one shape, and there's only these 5. There are no more to be found. They've proved that there's no more, and you can try to make some if you want. Like this one's made with pentagons. Try to make one with hexagons. You'll find they all sit flat down on the table. They never curl up into a ball. You have to put some pentagons on it, and then you get your soccer ball. So anyway, we've got the tetrahedron, the cube, and the octahedron. Those are the 3 simpler ones. And then there's the icosahedron and the dodecahedron. And these 3, you can divide them different ways. These 3 are all triangles. This one's square and this one's pentagon. And you can say these 3 here have 3 edges coming together at every vertex. And this one has 4, and this one has 5. The icosahedron has 5 segments coming together at every intersection. And you might ask yourself, well, what if I was to make 6? Well, try it. What you get with 6, again, it doesn't stand up into a ball. It doesn't come around into a ball. But don't take my word for it. You should try that out yourself. And these things are in nature. They're in molecules. They're in life forms have taken these shapes because they're valuable. And crystals also grow in similar shapes to these. Not just these, of course, but any geometric solid. So it's good to try to understand these. It's quite complex. If you were to measure these angles, three edges coming together on a flat surface, that'll give you 120 degrees at each one. But now they're also bent the other way, so there's a different angle here. And then, of course, if you set it down, there's going to be a different angle along the side here. And yeah, you can go arbitrarily complex in your analysis of the geometric solids. All right, so enjoy.